So let me show you a couple of examples. It's ignition coil, that's right? Yeah. Am I right? So here, that's just an ignition coil. You have a lot of those in the automotive industry. It's basically a transformer where you have a primary and you actually have an energy that goes through. You switch it off and it creates a big sparks of the secondary. The ignition is a magnetic circuit with an embedded magnet. So sometimes there is a magnet, there is not always a magnet, but sometimes there is a magnet and you have two windings. Primary winding is linked to the electrical drives. The secondary winding is linked to the spark plug. So whenever I have an energy that goes through the primary, I open the primary so the energy has to go somewhere, and it goes through the secondary, and this is how I get those big spikes. Pulse in the winding, so that's the source winding. Now, okay, we stop the current in the source winding, and then we get a pulse in the secondary. So what do we have to do? Presizing of the magnetic circuit, and try to find the best semiconductor to interrupt the current. Okay? So that's some of the things we have to do, but we want to look at it as a system level. So here is the main part. We have the car battery, we have the IGBT, okay, which is driven depending, it used to be spark, what they were called. I forgot the name. It used to be just little two pieces of platinum that when the rotor, the machine, the motor would turn out, it would open them. That's how it used to open the circuit. You know what, I don't remember the name of it. But anyway, so now it's actually done through a semiconductor. So it's actually better controlled, because before it was always associated only to the rotor, to the motor rotation, and it was difficult to change the angle of starting. So now, depending on the temperature of the machine, you can fire the IGBT earlier if it's cold, and later if it's warm, whatever. That's the magnetic part. So we have a little magnet right there. In yellow, we have the circuit, and we have the coils right around. So in Portunus, we can do this in different way. So we can do the driving circuit directly from the electrical network, and the magnetic circuit. So the driving circuit is always going to be the same. Huh? We basically have the battery, we have the engine that controls the IGBT, and we have here the current that goes through. So this needs to be connected to whatever goes to the magnetics. So for the magnetics, we could do a magnetic circuit. There is such thing inside the, well, just by continuing this. So we have the primary, the secondary. We have the spark plug, well, we have the resistance on the spark plug and the capacitance. Okay? Or we can do by block diagrams. So instead of the circuit, now I'm bringing those two information here. I have an interface that's going to look at the coil voltage, and it's basically going to do the same computation, exactly the same way. Or I can do with a reluctance network. There is a reluctance, all those elements exist inside Portunus. It's in the magnetic library. So I can have a coil, primary, secondary. I can have a nonlinear, it's a nonlinear reluctance. So the left reluctance of, if you remember, we had the central part, we had the core that was closing around. So we can have the central part, we can have the closing here, the magnet which is included right there, and then behind again we get the plug and the spark. So all this middle part can also be by reluctance. So we saw equivalent circuit, we saw block, we saw magnetic circuit, and now we can do with flux 3D co-simulation. So out of there we're going to bring the current, and same here, we will have the voltage and the current. So basically what we do is actually we bring the current inside flux, it gives us back the voltage, and so that's how we do the co-simulation. So right in the middle, I have the full flux things. So of course, if I look at those different approaches, this one is probably the fastest, but the less accurate. This one is a little more painful because I need to do all the block. I need to fill up all the blocks. This one is a reluctance network. It's not too bad. Maybe it's actually pretty good. And this one is, of course, the top of the top because now I'm having the full device. I can even include eddy current. I can include all of those things, proximity effect, and other things like this. So the electric driving circuit, we have the battery. We have a model for the battery. The engine, it's just a matter of defining how fast it goes and things like this. The IGBT diode, we bring it from the SPICE model. We just took the IGBT netlist that is provided by the manufacturer of the IGBT, so we don't have to do anything. And yeah, the command is just in the lookup table. So the very simple model, this is just the with the electrical circuit. What did I do this here? The one in turn ratio is taken into account. We just put the number of turns on both sides. The transformer iron losses can be estimated, but you have to do another computation on top of it. Of course, this is the block diagrams type of things. So if you do the block diagram, you only have the primary winding, and then everything else is done after inside the block, the different blocks. So you're going to have to describe all the magnetic behaviors through different blocks. And here they are. So we have the parent magnet, we have the magnetic core, and the coil voltage. So this is where we come in. We have the coil voltage, the resistance, and all of those things. So that's actually quite a complicated part because you have to, well, it's not complicated, but it's painful because you have all those blocks. We prefer never to do this kind. And then all the reluctance has to be a table, an equivalent table. So anyway, we have all those different elements. That just explains the different elements inside there. This is the magnetic circuit. So here we just have to fill up those information. And by the way, to get those information, maybe we need to do a flux computation because we need to compute inductances and stuff like this. And then finally, the flux model. And what I want to show you is the result. And here they are. So this is the current on the primary winding. So we start filling up the current, and then we turn it off. Equivalent circuit, that's where it gets here. Reluctance network, you can see I told you it's pretty close actually. And flux release, this is the full complicated simulation. Now, the important part here is that this computation takes a long time because we have to actually do compute the finite limit at every time step. Okay? When the two others are actually quite fast. So when we look at this, we say, okay, I have no reason not to take one or the other. However, this is on the secondary winding. So that's where we turn off the primary coil, and this is the spikes we do get. So the equivalent circuit, you can see it's right there. So we are missing some information in the energy transfer on the equivalent circuit. This is when we just do circuit and nothing else. The reluctance network, well, it's pretty good, and we'll do a little detail here so you'll see the difference. And the flux release. So before it's all the same, after it's all the same, but right at the transient, that's where there is a big difference. Equivalent circuit is not going to be good enough because we don't get the full spark. So we cannot do the full design. Now we need to see what the difference between the reluctance network and flux to see if one is better than the other. And so if we do a little, if I do a little zooming inside there, so the scale is different, you can see this is the equivalent circuit, this is the reluctance, and this is flux. So now it's a call you make. What's more important? speed or accurate result. If you look at this here, you probably have a good estimate of the total energy. This one, not at all. But this one, if you do the integral under this curve, maybe it's pretty close to this one. However, you don't get the peak voltage. Okay? So it really depends what you're interested in. But what you can say is that the reluctance network is definitely a very good solution.